And we're live. Hello. Welcome to another beautiful day of CS 435. Networks and cybersecurity is still deep in the networks part. Touched on a couple cybersecurity things so far, but we are still learning about networks for the most part. So, hello everybody. Happy Monday. Thank you for all the beautiful emojis. Everyone finished the UTF homework? You might wonder why there are so many different kinds of character encoding. And one of the main reasons is, of course, because of those stinking languages that use all those symbols. And I'm referring, of course, to emojis. Haha. Got you there. No, but when it was only the Greek and Roman and traditional alphabets of the few European languages, UTF-8 was more than enough to hold all the possible characters that there are. As we gradually decided that we wanted more characters, we had to invent new encodings. UTF-16 is still probably the most commonly used. It's got enough to hold, as many characters as one would reasonably need. As many of you noticed, they're quite difficult to read by hand because the number of bytes used for a character might be 2 or 4, I think. It's a complicated system anyway, so generally you're just going to use whatever UTF-16 decoder is built into your language. Hopefully the language you're using has one. And next time we're using Wireshark, just pay attention and look at what kind of, if you see any message with text in it, look at what kind of encoding Wireshark used to read it. So what do most people transmit over the wire? Obviously, you use UTF-32, you're going to use up a lot more of your precious message payload on unnecessary extra bytes. But if you are using a language or a character set that UTF-16 doesn't support, you're kind of forced to. So think about that. Think about how all those people abroad who use symbolic languages pretty much forced into sending everything by some larger character encoding set, right? So visit a Japanese website or a Chinese website or something that uses symbolic characters, not Korean. They have regular alphabets with letters like we do. So visit one of those symbolic alphabets and see what kind of encoding the traffic shows up in from those kinds of places. All right, so today we are going to continue on the network layer with good old DHCP. So let's see what the point of this is. So just to recap a little bit what we've learned so far, it should be obvious that most clients aren't connected to the public internet. That is, they're connected only to a router, so they don't have their own public IP. The router has the public IP, and the router does all the talking to the public internet for them. This is what we mean when we say that IP addresses, unlike MAC addresses, are not unique globally. So there's a whole set of addresses that's allocated for use just on your LAN. There are also other reserved addresses. You might have bumped into a couple already. There's a multicast and all these different kinds of testing addresses and such, broadcast, things like that. And there was also a couple of reserved MAC addresses, right? There's the broadcast MAC, and probably no one has all zeros, right? So there are reserved addresses all around. But in the IP addressing scheme, there are many reserved addresses for local area network use. That address, which is assigned to you by your router, is usually called your local or your LAN address. This is definitely a term that IT people use a lot, your local address, your LAN address. So that is your address given to you by the router. And then you also have your publicly exposed address, and that is the address of the router, and that's what everybody else in the world sees you as. The IP address, the local one, is used only to communicate within your LAN, and most importantly, that's to communicate with the router. Occasionally, you'll have to send network layer traffic to other machines on your network as part of the different assignments that we do. We're going to make different client and server applications, and we're going to talk to computers that are within our own network because all of you guys are going to be on the same CSVMs. And so those are still network layer packets, and those are still, let's call them datagrams. Let's be completely accurate. Those are still network layer datagrams, and those still travel within your LAN. But they are going between different computers, not just the computer and the router. So there are reasons that machines would need to talk within the network, as well as outside of it to the public internet. And just remember, keep in mind, routers are level 3 devices. They are network layer devices. And you can also glean from this why the company level 3, which is responsible for a lot of the backbone of the internet, called themselves that, right? Because they are responsible for the routing and the network layer of traffic between cities, states, nations, etc. So level 3, haha. All right, so when you connect to a router for the very first time, so you have just freshly connected to a LAN, we've noticed how you do that with ARP and everything when you're connecting to it on the link layer for the first time. And remember, we noticed that the link layer connections and the link layer communications don't require you to do any kind of setup. You can start talking right away because of all this different broadcast functionality and everything. You can send and receive messages the moment you're connected. There's no bootstrapping. Not the case for LAN, right? Not the case for IP. You're going to need an IP address before you can communicate. And so you need to get an IP address first so that you can talk on the network layer. So how are devices issued their IP address or their local IP address if they're connected to a router that handles the public one for them? And once you get an IP address, how long do you get to keep it? What happens when you disconnect or you go offline? Do you get to keep it while the machine isn't sending any traffic, while the machine is offline? Or do you lose it so someone else can use it? Those are actually more of questions for IT, so not really something you need to think about too much, but it will eventually probably come up for you as well if you're making networked applications. So, Dynamic Host Configuration Protocol, DHCP, is the most popular method for distributing network IP addresses. This is typically used by your home router, so your basic good old consumer router. It's used by enterprise and commercial grade routers as well to handle their local area networks. And it's also typically used by your internet service provider themselves to give you your public IP address, to assign you the one that you actually pay for. Now, of course, the ISP has a really powerful DHCP server and all this goodness. So as we go through this, you might think about this in terms of how your home router might do it. But also remember that ISPs have to do approximately the same thing, and they have to do it on the order of hundreds, thousands, maybe tens of thousands of customers, sometimes being served by a single DHCP server or cluster of DHCP servers. So think about that as well as we go through this. This goes from your tiny little sub-$100 home router to big ISP super DHCP server that handles maybe 1,000 requests at a time or something. I don't know. Depends how they set it up. And again, as with the other protocols that we've talked about before, there are other options. This one is just dominant. ISPs use a lot of other different methods. In the dial-up era, it was much more common to see PPPoE and other different kinds of setup. You might still remember those or see those settings in your router page and wonder what those are for. Those are for your initial IP address discovery from the ISP. And different technologies, so DSL, cable, fiber, whatever, they also tend to use different tech because the delivery of this IP address ultimately has to go to your modem first. Your modem has to figure out how to handle the physical connection and stuff to the service provider. And so as part of the bootstrapping of the physical connection and the link layer connection, sometimes they'll also handle the IP address. That's up to them. So something to think about. All right. DHCP is automatic once it's been set up and the server is running. Sysadmins don't have to do anything, so it's not like there's somebody sitting around giving you your IP address manually. That would be incredibly dumb. It allows us to support as many active online connections as we have room in the subnet. So if we have a /24 subnet and we can support 255 connections, plus 1 for the router is 254 connections available altogether. Then we can support up to 254 IP addresses with DHCP. This algorithm is really similar to ARP. You'll see a lot of similarities. There are definitely some extra steps, but you'll see a lot of tie-ins to ARP. And when we do the Wireshark lab on Wednesday, don't forget to sort by boot P, which is strange, right? Why not DHCP? No idea. Boot P to see DHCP traffic. Or, when we haven't learned about ports yet, ports 67 and 68 are used for DHCP. So those are the sorting methods you can use once we get to the lab. Okay, so first, a computer connects to the network and they would like to speak to the machine in charge of DHCP. So typically the machine in charge of DHCP is called the DHCP server. So you've just connected to a network. How do you know who the DHCP server is? Who do you talk to find the DHCP server is? At this point, remember, you have no IP address of your own. You have your link layer MAC. How do you know who to talk to get your address? So you first send a DHCP discovery message to broadcast. And you see, again, a big similarity to ARP, that it's sent to broadcast first. And you're trying to figure out who is the DHCP server that I need to speak to. Now, there is a broadcast IP, but technically it's, I guess you could say, meaningless, because network layer devices don't generally forward their broadcasts like link layer ones do. But anyway, broadcast IP, just like the broadcast MAC is all ones, which in IP form would be 255, 255, 255, 255. Remember, in MAC form, we represent it in hex, so it's FFFFF, but IPs we represent in base 10, so it's all 255s. And we set the source, again, very similar to ARP, to all zeros, claiming that we don't have one yet. And because you don't have an IP address yet, you can't actually talk over the network layer yet. So actually, this is broadcast over the link layer. So over the link layer, the destination MAC is also going to be all F. So it's going to be a broadcast. And since we're not connected to the network layer yet, and again, network doesn't actually have a broadcast feature of its own. It relies on the link layer broadcast to deliver these kinds of messages. All right, so that's your first message, your discovery. Let's look at some of the contents of that. So the payload of the discovery message is an application layer packet, a UDP packet, which we haven't learned about yet, and we'll get into those later. But for now, just think of it the same way you thought of ARP, that this is the payload of the datagram. So ARP was the payload of a frame. This is the payload of a datagram, and it has all these different fields. It also has a UDP header, but we'll just ignore that for now. So some of the fields that you see in the payload. You'll see the message type. This tells you if it's a request or a discovery, and this is a discovery. The first message is called a discovery. It tells you the hardware type, so overwhelmingly Ethernet at this point, but could be others still. It tells you the MAC address that you have, so this is a way for the DHCP server to talk to you after it has responded to your message, right? So once the DHCP server has caught your discovery, it will be able to talk to you over the link layer directly to your MAC address. This will also be in the sender field on the link layer too, right? So when you broadcast that message on the link layer, you'll have the recipient be all Fs, but you will also put your MAC address in the sender. So question, you can answer this in either chat. Is this a duplication? Why don't they just look at the sender field on the link layer? Why don't we just look at the MAC address at the sender field in the frame? Why do we have to repeat it here? This is an important concept. We've seen a couple times things getting repeated, right? We saw in the header for the datagram that there's a type field again, right? Even though there was one in the frame. We see that there's a repeat of the MAC address here in the payload of a datagram, which is level 4, even though there was already information you could get at the Ethernet layer, right? So why do we have physical address here again? Why don't we just look at the sender one? So see if you have an answer in either chat, and we'll get back to it. Someone answered to make sure the device is still there. Not necessarily. We could have checked if the device was still there on the link layer as well. We could it's a duplication of the same info, so it doesn't help us identify that it's still there extra. We're going to have the MAC in the sender field at the link layer, but we're also going to have it here. Why do we have it twice? So you'll also see your requested IP in the discovery message. So if you've already been connected to the network before, generally the common practice is to ask for your old IP back. So remember we saw those ARP probes previously. When we were looking at ARP, we saw those probes. So probes might go out after this type of request. So if a IP address is requested, either the router or you, either way, will probe the network and see if anybody's taken your IP, so if anybody's squatting your claim. All right, couple answers. Someone asked, does the redundancy add an extra level of certainty? To an extent, but insofar as we have error checking, we shouldn't have a need for that kind of certainty for one field. We already have two kinds of error checking at this point. We have the checksum in the datagram header and the CRC at the link layer. And someone also said even more error checking. So it's actually not error checking, and it is completely redundant. And the reason is something that we'll see again at the next higher layer too, is the concept of encapsulation. So when all of these different schemes were designed, one of the primary goals was to make sure that DHCP, for example, would operate no matter what kind of link layer traffic it was transmitted over. And so Ethernet is dominant now, but at some point there were alternatives, and in the future there still might be alternatives. And so every layer has, inside of its headers and inside of its payload, all of the information that it needs. Layers are never supposed to reach into the layers below them for information, because that violates encapsulation. And if down the road we decide as a society, as a world, to change the underlying schemes that we use to transmit our stuff, let's say on the link layer, well, then you would have to somehow update this system as well. So you'll see that concept again, the concept of encapsulation, that everything that this protocol needs to operate should be available in its headers and payload without having to reach into the layers down. You will occasionally reach into layers above, but you try to never reach into layers below for something that you need to operate. And the last thing that you see in the payload is a transaction ID that's basically a one-time random number, which we call a nonce, and that's chosen by the discoverer. Okay, so when a DHCP server gets the discovery request, where does it send the reply? I'm going to leave this open-ended, and we're going to see it in the lab on Wednesday. So it has the sending address of the sending MAC address of the machine attempting to connect, right? So does it send the reply to that address on the link layer, or does it broadcast it on the link layer? We'll see. And what happens if there's more than one DHCP server responding? Large organizations can have more than one. So the next message is going to be called the offer. But this message is also going to be broadcast on the network layer, so I'll give away part of the answer, because the client still doesn't have an IP. So as far as the DHCP payload is concerned, it's still going to be all 255s. So the question is, what do you think it's going to be on the link layer? Is it going to go to broadcast in the link layer, or can it now be addressed to that machine's MAC specifically? The transaction ID that we had before, that one-off random number, allows clients to tell if multiple DHCP servers have responded. So in a big company, they might have a large building, and so if the DHCP server is like physically far away, sometimes they'll decide, well, we'll put another DHCP server on the other side of the building, so clients on that side of the building can connect faster. Typically, this is less used today. You generally just have one large DHCP server. And same for your ISP. They might have more than one DHCP server. In that case, it's important for redundancy. If you have a standalone DHCP server, it's often a good idea to have two, because if one goes down, nobody can connect to your network. That's terrible, right? So you really want to have that running all the time. So a little redundancy there sometimes is tolerable. Clients will typically accept the first offer that they get, because that's the fastest, right? So the offer, again, still broadcast to 255s, and the source, rather than being zeros, is now the DHCP server's IP address. So now the original discoverer knows both the IP address and the MAC address of the DHCP server once it receives this reply. And the most important parts of the payload here, DHCP messages have very long payloads, by the way, so I'm just highlighting the big important parts. So the most important parts of the payload are the offer IP address, so the one that the DHCP server is saying that you can have. So we'll offer you a IP address, and this is where you get it. It'll give you a lease time, so how long it's good for. Typically it's just a few hours. This is configurable by the IT department, but typically it's a few hours up to a few days. And then it'll also tell you a renewal time in addition to a lease time. So much like many subscription-based services or registrations in the real world, like for example your driver's license, you have the date that it expires at, and then you also have the date that you are first able to renew it. So I think it's a month before it expires for driver's licenses. So same thing for IP addresses. You have the date that it actually runs out, and then you have the first time at which you can actually renew it, how long you have to wait until you can ask for a renewal. And so typically you're not going to wait until your driver's license expires to renew it, unless there's a pandemic and your license was extended until the end of the year. But typically you're not going to wait for it to expire. You're going to renew it during that renewal window. And so both of those pieces of information are going to be conveyed to you. And again, you're going to get a transaction ID. Okay, so the client gets that offer, and then they send back a request. This is very confusing, okay? Everybody forgets this. I'm sure you'll probably forget it at least once. But just try to remember, okay? Discovery, offer, then request. Okay, normally it's request, then offer, right? That makes sense. No, discovery, offer, then request. Stupid order, I know. And they should have probably renamed these messages, but the request comes after the offer. So the client gets the offer, typically picks the first offer that they get, and then sends a DHCP request for the address that was offered to them. Okay, so this is now directed to the DHCP server's IP. It's now known. After getting that offer, we know both the MAC and the IP of the DHCP server. And now we technically have our own IP address after this, right? So another thing to think about, what's in the senders field here? Is it going to be the IP address that was just offered to you, or do we still put it as zeros? We'll see when we get to the lab. The server responds now to the new client's IP. At this point, once the the request is received, everything is set up, but the DHCP server sends one final response to the client's new IP address and confirms that everything is all set. This is called the ACK, or acknowledgement. So that's DHCP. All right, that's what we're going to look at in the lab. And that is how almost all IP addresses in the world are assigned. So think about that again in terms of a large internet service provider with lots of customers, how they would do it. They would do it pretty much the same way, using that DHCP process. What is the server typically in a smaller network, like in your home network? Again, it's your router. The router is the workhorse of the home network. So inside of your router is also all the necessary hardware and software to perform DHCP. Right? So your router does your DHCP, your router does your routing. Your router has all kinds of jobs. Now, in a larger organization, like maybe John Carroll's campus, there will probably be a dedicated DHCP server, and this is because you don't want to, again, overload the router, because the router's primary goal is switching quickly. Now, one thing you have to worry about with DHCP servers is if there's an outage and everybody gets disconnected, then when the network comes back online, the DHCP server is flooded with requests in an organization, right? You get thousands of devices trying to connect at once. And so DHCP servers often have this unfortunate, very, very low usage. So the DHCP server uses like I don't know, like 10% or 5% of its resources on an average day, because you need to have a lot of extra resources available for when the network goes down and it needs to quickly come back up again, and there's thousands of things DHCP is serving. So the DHCP server is usually overbuilt for its purpose. Someone said that we have a single Windows server DHCP server for John Carroll, so that sounds about right. Yeah, just one. At any given point, we probably have something like 3, 5, maybe 10,000 network devices connected. So you're looking at a single, normal, probably not particularly super high-end hardware distributing IP addresses to thousands of devices. And of course, we're no strangers to outages, and after there's an outage, you normally come back online pretty quick, right? So it must be configured in such a way that is good for that too. So now let's look at how it is that devices can talk to you when they only have the public IP of your router. This is one of the most annoying systems in all of networking. It's extremely complicated and irritating, and if it didn't exist, it would be better for everybody, so hopefully IPv6 gets rid of it very soon. And that's the concept of NAT, network address translation. So this is something you need to know about as a developer. You need to be keenly aware of it and how to work your way around it, because it causes you to have to do quite a few workarounds. Hopefully in the next decade or two, as we transition to IPv6, we will no longer have to worry about NAT. But for now, as a developer, unfortunately, it's something you're going to have to need to know. So unlike most of the other stuff we've covered so far, this is something you really do have to be aware of as a developer. So we've learned how routers assign IP addresses, so using DHCP or something similar for your internal subnet or LAN. We've learned that your ISP can also do a similar thing to assign your address, so your ISP might have its own DHCP services. We also know that typically the public IP address, the one that you are paying your ISP for, has a bunch of different devices behind it. It might have your phone, your computer, a bunch of other computers, a bunch of other phones, whatever. And so there's some way that you all have to share it. We know that there's definitely not enough IPv4 addresses to go around. The world is already running very low, and so everybody has to share one public IP, and until IPv6 is standardized, there just aren't enough addresses to go around for everyone. And that brings us to network address translation, which allows multiple devices to share a single public IP address. To the outside world, every device that's on a NAT, and we just call it a NAT usually, as in a subnet that is administered by a router where all the devices are using network address translation. We'll typically just call that a NAT or a NATed LAN, something along those lines, but a NAT works. So to the outside world, NAT looks like a single device talking to them. So all the computers on the network that are talking look like a single device. So if all of us connect, let's say from John Carroll, we all connect to Google at the same time, it looks like one device connecting to Google a bunch of times on their end. Okay, just the different ports we'll see. All right, so there are several IP address ranges that are reserved for local area network use. So again, this is what I mean by that they're not globally unique. And these are probably the IP addresses you are most familiar with seeing. You've probably seen the 192.168.0.0 range, because that is by far the most popular for most home networks and small networks. So that -16 range is usually the one that's built into every home router. So usually your IP addresses, everything on the network will be 192.168.0. The router will be .0, the first computer will be .1, the next one will be .2, the next one will be .3, and so forth. Some places, even some residential routers, are configured to use 10.0.0.0, but /8 is an enormous range. It's super unnecessary to have that many addresses. -16 is way more than anybody needs in a normal setting. Occasionally you'll see the mid-sized one, the 172 one, but I don't think I have ever actually seen that one outside of a textbook. I don't think that one's really used much anymore, so we're not even really going to talk about that one. And so the basic principle, it goes like this. You have your public IP address that's exposed to the internet, so 125.3.5.4.8, whatever, and then internally your NAT server is 10.0.25.1. This guy handles all of the NATing. He's probably a router as well. And then the different devices on the network are 10.0.25.11, 12, 13, 14, and so forth. So they all have their local IP addresses, and the NAT is responsible for administering them. Same here, but here we have the 192 addresses instead. So your NAT's probably going to be 192.168. In this case, they're using the .1 band, so it would be 192.168.1.0 would probably be your NAT server itself, and then the first host is .1, then 2, then 3, then so forth. Actually, they have the server here, and they've decided to put the server at 192.168.1.100. You don't have to put the server at .0 or at .1. You can give the server whatever IP address you want. So, and give it 100, give it 100. As long as it's within that range, everybody will discover it through DHCP discovery, assuming that it's your router as well, or there's another system for discovering it if it's not. So there you go. Doesn't matter. Pick your IP address as you wish. But first, in order to understand NAT, we've got to jump into the transport layer for a minute and talk about ports. Ports are actually the main feature of the transport layer, so we're going to talk about them a lot more later. But we're just going to jump to level 4 for a minute here and talk about ports, which again are part of the next layer up, the transport layer, not part of the network layer, so don't get them confused. But NAT and other algorithms use ports. You've seen DHCP uses ports as well, even though it's considered a network layer protocol. Now, the implication of the fact that those things use ports, DHCP and then NAT as well, is that traffic that's level 3 or below can't penetrate anything that's behind a NAT, because if it doesn't have the port, it's not going to get through. So that means no ARP with anything behind your router, right? Because no more link layer there, and that's why it's the end of your LAN. If you wanted to ARP with something beyond your router, it would be possible for the router to rebroadcast the ARP on your behalf. So if the router wants to pass along link layer traffic like a switch, it is actually possible to ARP beyond your router. And remember that DHCP again also sends a payload that has ports. So level 4 messages, transport layer messages, are addressed not to just an IP address, but also to a particular port. This is what allows applications and the operating system to actually use the traffic that arrives, right? Because although you have an address, it would be very annoying if all of the traffic just went to the address. Ports are just points of entry in your machine where messages can get through. And they're totally abstract. It's not like there are different like physical channels or physical layer channels. They don't go over different NICs. They don't go into different traffic slots. They don't have different slots of timing or anything like that. They're completely abstractions. They're just numbers. And it's not even like channels like on a radio or on a television or something, because they're all used simultaneously. But they allow the receiver to differentiate where they're supposed to put this traffic. So if you want to talk to 123, 123, 123 on channel 40, that would be one port. Channel 41 might be a totally different conversation. Okay, so this allows the host to distinguish between other communications on your channel. Let's use a couple metaphors and hopefully it becomes a little bit clearer, right? So you have your house. Your house has an address, okay? And there are many ports of entry on your home. So we're using the definition of port not as a shipyard, not as a place you plug something in, but as an entryway, all right? So your house has many entrances or potential entrances, things that could be opened. It also has many ports that are permanently closed, called walls, right? You can't open those ports at all. But your house has doors, windows. They have different levels of security as well, something to think about. Your door is able to be open and closed, and people can come in and out of it, as well as packages and such. Your window generally is not configured in that way, right? Your window allows air in, but not insects, hopefully, if you have a screen. There are all kinds of different layers to this metaphor, but the security is the big one. And the port that's most open to our homes is probably the mailbox, right? Because the public, well, not the public, but the mail service gets to use our mailbox and stick mail into it. Some of us also have a even more publicly available port in terms of a public mailbox. Maybe you have a newspaper mailbox or something. Anybody can shove messages for you in there. But most of the ports to our house are closed at any given time. Okay, so we can think of closed ports as firewalled too when we cover firewalls later. I think this expression also inherits a lot from the sally port. A sally port is an entrance in a wall where people can come in and out. So obviously walls have gates too, where large bodies of people come and go. But you need to be able to send out small numbers of people in order to do maintenance and scouting and what have you. And so ancient walls often had small doors leading to either a staircase or a small hallway where just one person could get through at a time, so that you couldn't just attack the sally port. They would have these small doors where a couple people can get in and out to do whatever it is that they need to do outside the wall. And it's the same thing with network ports. You have small holes in the wall where messages can move in and out. So back to NAT. Again, another metaphor. Let's say that a NAT is a little bit like a post office box or a public mailroom, something you might have in an apartment or something. So every individual client gets mapped to a port, but everybody shares the same address. So you're all at the post office at 123 Post Street, but then you also need to specify which PO box you want to talk to if you want to talk to a particular person. And that way, there's no interference between all the different people messaging each other. So if you want to talk to Bob, it goes to Bob's P.O. box. If you want to talk to Steve, it goes to Steve's P.O. box. If you want to talk to Susie, it goes to Susie's P.O. box. There's no overlap between their different messages because they go to different boxes, but that whole concept is completely an abstraction. All those messages have ended up at the same place. We've just chosen to get a bunch of numbered boxes and put those messages into different ones. And NAT is the same way. So how can we split your public IP address? Let's say that host A in this scenario is behind a NAT, and host 1 may or may not be, it doesn't matter, but host 1 is somewhere out on the internet, and A is talking to them. All right, A is at all 123s, 1 is at 123.0.0.0.0.1. Okay, so host A's router picks an arbitrary port that it wants to use to talk to host 1. So in this case, we are assuming that host 1 has some open port available to speak to. Host A picks an arbitrary port to talk to them, let's say, for example, 1050. This is the outgoing port on host A. Host 1 doesn't see host A at all. They see a device talking to them on port 1050 coming from IP address 123.123.123. So A probably has their own local address on that network, right? But 123 is their public IP address. That's all host 1 sees. They don't see the local one. They see the public one, and they see the traffic is coming in on 1050. Host 1 decides to send traffic back on, let's say, 1051. The router figures that out, and now it knows that anything that's inbound on 1051 has to go directly to host A. So anything that's outbound on 1050 is being sent from host A to host 1. Anything that's inbound on 1051 is directed at host A. And that's the really basics of how NAT works. Okay, so in this case, host A's public IP address was 123.123 or whatever. Their private IP, their local one, might be something like 192.168.0.2, and the router might be .0. And then host 1 has a public IP of 123.0.0.0.1. So in this case, the source and the destination would be respectively 123.123.123 port 1050 for the outbound communications from 192.168.0.2. So the router knows that anything that's going outbound on 1050 comes from .2, and anything inbound on 1051 should go to .2. And so the router will forward all the traffic to the appropriate host in that case. Now here are the big limitations for you as a developer is that sometimes, in fact most of the time, you're going to write your services, your programs, in such a way that they have to operate on a specific port. So web, for example, has to run on port 80. That's because when you connect to a web server, you always try to connect on port 80, or actually 8080 is another option as well, but seldomly used. So you try to talk to the web server on port 80, you wouldn't just try every other port that there is if they didn't respond on port 80. You would just know that they don't have a web server running if they don't respond on port 80. So because web servers have to talk on port 80, NAT means that there can only be one web server behind a NAT, if any at all. And so if you have a very large network, like let's say John Carroll's, and everybody shares one public IP address, there can only be one web server. That would kind of suck, right? And same with your home. If you have a web server set up somewhere, you can't set up another one. You just have to use that same one to host multiple web pages or websites or whatever. So that matters a lot to you as a developer, right? If people have their ports blocked because they're behind a NAT, you have to find some way through them. There's a large body of work figuring out how to deal with NAT and all that good stuff. It also causes some overhead on the router level because the router needs to now read level 4 headers. It needs to read ports. That violates the OSI model because the router is supposed to be a level 3 device, not a level 4 device. It forces the router to peak a level above, which it's not supposed to do. Remember, we're supposed to have encapsulation. Everything that we need is supposed to be available on that layer. And it adds overhead to the router. So developer headache, overhead, a lot of different problems with NAT, but unfortunately something that we have to do because we're out of IP addresses. All right, so let's say that you do want to be able to use your web server behind a NAT. Let's say that you want to be able to open up port 80 to a specific machine. So a specific machine is going to be your web server. So in order to allow a specific machine behind your NAT to host some service, let's say again on port 80, you need to tell the router to forward the port. All right, and really your IT department has to, although at home you're probably your own IT department. So if you have a service running on port 80, you are going to ask the NAT administrator, the router in general, to forward anything that's coming in on port 80 to you. And obviously that can only be done for one machine. So anything that's inbound to your public IP address on port 80, you can forward to just one machine. It wouldn't make sense if you could forward it to two. So you're going to forward anything coming in on port 80 to, let's say, 192.168.0.2, and then .2 will be your port 80 web server. Now again, only one machine can get a forward to each port at a time. We also have universal plug and play, which was used to simplify some of this port hosting. Sometimes this will work for you as a developer, sometimes not. In my experience, this created more headache than it solved because in your directions, your tutorial, your how-to or whatever, there's always this big old guide on do you have UPnP enabled, go check your router settings, blah, blah, blah. So it's kind of more of a headache than it fixes. But anyway, let's say that you, a developer, wrote an application that operates on port 400, okay, and it needs to talk on port 400. The application does. It expects traffic coming in on port 400. So you ask your NAT, instead of forwarding port 400 to you, let's say port 400 is unavailable for some reason, your NAT will map it to 5000 on the public IP address. And so the traffic on the outside will talk to you on port 5000. But when it comes in to your machine, so after the NAT gets it on port 5000, it will send it to you on port 400. Okay. That allows your application to work. Or, because your application is aware that you're behind a NAT, it advertises port 5000 instead of port 400. So your application is NAT aware and advertises the forwarded port that it got. So again, probably more confusing than just forwarding the port, but forwarding the port is not always an option. Sometimes you're not even allowed to forward the port, right? So we have, I think, long enough to start on ICMP, the Internet Control Message Protocol, another of the very important protocols on level 3. Again, it has a payload, so technically it's not strictly level 3, but just like ARP had a payload, we also consider ICMP to be level 3. This is probably the most important protocol to devices like routers because they use this quite often in order to exchange simple information with one another. Obviously, it's called the Control Message Protocol. It's used for simple messaging. Okay, so the most popular kinds of ICMP messages. All right, there's the ping, the echo request. All right, so an echo request is simply, here's a message, please send me one back. And then the echo reply is, okay, here's your reply. So if you want to see if a IP address has a functioning, working machine at it, this is the easiest way to do it, right? So you don't know what ports they have open, but most properly configured machines will respond to echo requests. So echo requests arrive typically in their own special slot, and you can, as a sysadmin, decide, are we going to reply to echo requests or not? Most machines still reply to echo requests, although as we'll see down the road, this can create a cybersecurity headache, and so many sysadmins are starting to just say, nope, we're just not going to respond to ICMP messages at all. But if everything's working correctly and all people are good, anytime a server's online, you should be able to tell by sending them a request. They will reply to you. You might also get a destination host network protocol port unreachable. That is that the network could not find a route to where you are asking it to find a route to. So if you try to ping something and your network cable is not plugged in, you'll get one of these because it'll say, couldn't get your ICMP message there because you're not connected to the internet. But you might also get this in other situations where a IP address is unreachable for whatever reason. So it's possible for an IP address to become unreachable or a port to simply not be open. And then in that case, you'll get one of these destination unreachables. This is also what you'll get probably if they have turned off their responding to requests. You'll just get a destination unreachable instead of a reply if they've decided not to respond to requests. Remember, we have this time to live field in the datagram header. Every time a router gets a message, it subtracts 1 from the time to live, and if it's gotten to 0, it discards it. Well, when it discards it, it also sends one of these, a TTL expired message back to the original sender. It tells them your time to live expired, I'm the person where it expired, or I'm the router where it expired. Here you go. So once the time to live on a packet expires, your polite router that's not particularly busy will send a time to live expired message. If the router is already overloaded with other traffic, it will usually still send one of these because the overhead is very low and because ICMP messages are typically considered high priority. All right, so you could also get a bad IP header, something corrupted or something went wrong in your datagram header. You don't typically see a lot of these. And then routers will also advertise and discover each other and all this other wonderful stuff over ICMP. We won't get into too much detail with that because it's very complicated, but other control messages as well. These are just the most popular ones. So that brings us to traceroute, which is a common tool you've probably used before in your own network. Let's say that we want to trace the path that our traffic follows across the internet from our device to some faraway device on another network. How do we implement this using simple echo requests, right? How do we trace a route to a faraway device using simple echo requests? Well, all we have to do is send an echo with the time to live of 1, then 2, then 3, then 4, and so on and so forth until we get one that reaches our destination. So we send traffic with the destination set to the place that we're trying to do a traceroute to, but we change the time to live from 1 to 2 to 3 to 4 and so forth, and every router along the way that is properly configured will send you a time to live expired message, and in that time to live expired message will be the IP address of that router. So you will know the journey that your packet took by examining those time to live expired messages. And then once you get a reply back from the endpoint, you know that you are finished. You have plotted out the whole route. So on the TTL1, you will get the TTL expired message back from the first router. On 2, you will get it from the second router, and so on and so forth until you have mapped out every hop along the way. And you can give this a shot by just typing traceroute and any IP address or something like google.com into your command line, and it will send these TTL messages one at a time and show you who responded back to each one. So it's very useful for diagnosing route-related problems. All right, so next time we are going to do the DHCP lab, and we might finish up with the network layer here, and then we're going to move on to the transport layer in earnest. So don't forget your Homework's due Wednesday. And that's going to be it for today, guys. Thanks for tuning in. See you on Wednesday.